Okay, I think we should just go live. Okay, so Jerome, Petazzoni. Is that good? All right.
Your French accent there, Jerome?
That's right. I'll just hand it over. You got your mic, so you're free to go.
Hi. So, thanks for making that a full. It's really exciting. So recently I gave a talk about Docker and something that we call separation of personal concerns. It's another topic, and the conclusion was that that made Docker extremely convenient for microservice architectures and immutable infrastructures. So when I was asked to talk specifically about Docker in the context of microservice architectures, it was kind of convenient. But this time, instead of starting for like the technical basis of Docker and going all the way to, and that's why it's convenient for microservices, I will go the other way around, start from microservices and kind of go from there. So do like from the top to the bottom rather than from the bottom to the top. So, okay. Containers, Docker, and microservices. So that's me. I'm French, as you might have guessed from the accent. And I work for Docker, and one of the things I do there is that I run pretty much everything inside of containers, and I help other people to do that. I will talk more about running everything into containers later in the presentation. And I also dabbled in microservices because before Docker was Docker, it was .cloud, platform as a service company. And I built and scaled that, and we had a number of services, and we built that 40-something years ago. So we did not call that microservices, but by looking back, that was definitely microservices. The platform had more than 100 services, including load balancers, code builds, code uploads, monitoring, logs, and so on and so forth. And to find out exactly how many servers there were, I actually went to the repo and went to the service discovery module and counted those services, and it was 106. So that gave me an idea of all the challenges that come with microservice architectures, and then thinking back, I was like, well, it would have been nice if we had started by having Docker from day one, because instead we had to build something else, and that was rather painful. The picture is because back then I was in the ops team, and we were on call 24/7, and very often I would be paged in the most uncommon places. So this is like we're trying to get drinks with coworkers, and on-call pages me, and so I end up fixing servers instead of having drinks. And we have countless of pictures like that. I'm glad that I'm not on call anymore. So the outline for today, we're going to quickly do a kind of a recap of what are microservices, just in case some people don't know, or at least so that we can agree on the definition. Then we will discuss the challenges that come with microservices, and then we will explain how Docker helps with that. And then I will give a kind of a fast track to get started with Docker in that context. And then we will do Q&A to extend, of course, to, for instance, Kubernetes, as we said before. So first, why people are doing microservices? Well, I guess it won't be too hard to convince you, but just as a reminder, the idea is to break down big, huge applications into many little services. And so one random example is when you do some e-commerce website, instead of having that big website and each time you roll out some little extra button or feature, well, instead you break that down in many little microservices, small independent applications. So you end up with a web front end for sure, but that web front end should never ever touch directly the database or really do anything. It should just talk to the other modules, typically through APIs. So maybe you have something with the catalog of the products that you have, with the pictures, descriptions, and everything. Then you have something to manage the inventory and stock, but that thing doesn't have the description of objects. It just has like object numbers, and it knows that there are 20 of that article in that warehouse in Kansas. You can have another module for shipping, another for billing, another like a recommendation engine, and so on and so forth. So the whole point of that, well, there are a number of advantages. One of them being that you can pick different languages, different frameworks for each little piece that you have. Like maybe you have a chat module and that's synchronous, and so Node.js is a good fit. But maybe the billing code is using some Java enterprise stuff, and there is no way that this is going to be in a different framework. So having those different services lets you pick the best tool, the best framework, the best programming language for the right job. It also helps you to replace components and refactor them in a less risky manner. If you just change the recommendation engine, you're just touching that, so you're not going to break anything else, and you can have a team working on that refactor without impacting the other teams. It also means that instead of deploying everything and having to coordinate with everybody to ask them, okay guys, is your part of the repository kind of clean and ready to deploy today, or should we wait tomorrow because right now you're in the process of fixing something? Well, instead, each team can deploy whenever they want without having to wait and coordinate with other teams. Which means that eventually you can deploy more often. Instead of agreeing on, okay, let's deploy every Wednesday, you can, and then every Wednesday everything must be clean, like the master branch in your repo must work. Then each team can deploy whenever they want. If they want to do a continuous deployment and deploy every hour, that's fine. It also helps to implement something that Jeff Bezos called the 2-pizza rule, which means that no team should be that big that it needs more than 2 pizzas to feed them. So that's basically maybe 6 or 7 people, depending on how hungry they are. But the idea is that if you have more people than that, then communication overhead becomes some kind of an issue. Because you spend more time talking to those people with whom you don't work that much to sync up, rather than this with small team and of people that like kind of are tightly close together and know exactly what is going on. So that way you can have ownership of services. There is that team, those people work on the billing code. That team, those people work on the search engine, and so on and so forth. Some people can be part of multiple teams, that's not a problem. But at least if you have a team of 5, 6 people working on search, it's their thing. It's not 50 people in the company and there is more or less that person who is more or less of a guru on the search code, so we ask him whenever. No, it's really a team owning a part, which helps to implement responsibility on that. When the service breaks, it's not globally the team of 50 engineers is like, well, we screwed up, what should we do? If there is a team of 5 or 6 people and they are in charge, they are responsible for that service, and they feel concerned by what happens to that service. And if you want to put things farther, you can even put that team on call for their services, which is supposedly what Amazon does. When, as a developer, you ship code and if it breaks, it wakes you up, which gives you a pretty strong incentive to ship code that works. So what's the challenge with microservices? So I borrowed that slide from a previous presentation in that group because I was trying to see what had been the previous conversations. And so it all revolves around the complexity of deploying and operating a distributed system, because now you don't have one big block of software, but many little services that have to talk with each other, and it becomes kind of a challenge. There is a blog post, Microservices, not a free lunch, that expands on the downsides of microservices, but let's pretend that everything is nice and not concern too much about that. Let's see the issues that we will not address today. Well, first, if you're going to do microservices, you need something fast and efficient so that the services communicate with each other. We are not going to talk about that. We are not going to talk about what's the best way to break down applications in smaller parts. Sometimes it can be complicated, but we're not going to talk about that either because it's not related to Docker and containers. We could have talked about service discovery and load balancing, and I will be happy to talk about that in the Q&A. But I wanted to really concentrate on this, which is the fact that when you do microservices, instead of having one big app and so deployment is just like one deployment and it's done, now you have 40, or in the case of .cloud, 106 services to deploy. So it's much more work to deploy that stack. Even just deploying it like for a test or a dev environment, it's deploying actually more than 100 pieces of software, so it's a lot of work. And one of the upsides was, right, now you're free to deploy whenever you want because you are an independent team and you don't have to synchronize with the other guys. Right, but that means that it gives you an incentive to deploy whenever you want, so more often, which means that your deployment process must be fast. If it takes hours to deploy, you won't be deploying every hour, otherwise you will only do deployment. It must be reliable. I mean, if 50% of the time when you deploy you break stuff, you won't want to deploy so often because each time there will be this kind of, this will break, I don't want to do it. So it must be fast, it must be reliable. You must be confident that when you deploy it will work all the time, and it will be automated. That's kind of a consequence of the first two. It must be as easy as pushing a button and the code kind of goes directly from the repository to production. So how do we do that? Well, we can use containers in Docker, and this is how and why. So the big picture is like the motto of Docker is to build, ship, and run any application anywhere. And so I decided to take that and break it down in little parts, microservice type, and see exactly what each of those words mean in the context of Docker and how that helps. So first, build. That means packaging application in a container. So it's like when we build package distribution, package for distribution, but instead we will build a container. A container is the new package. Ship, that means once we have built that, we want to deploy that on our servers, and so we have to have an efficient way to do that. Run, well, that means that we have to actually execute that code, and we have to execute it in an efficient way. Any application, in that case, that means anything that runs on Linux, and I will give some details about what can and cannot run inside of containers. And anywhere here means that when you put stuff into containers, those containers can run on this laptop, can run on your laptop, because even if it's a Mac, we have VMs to work with that. It can run on cloud platforms, public or private. It can run on bare metal, physical machines, and so on and so forth. So let's see in detail. Build. What does the build process look like? So let's say that we're looking at an extremely simple microservice, which is just a kind of hello world web server. And so the way that Docker does the build is through something called a Dockerfile. A Dockerfile is a recipe explaining how to actually build a container. Just like a makefile gives instruction to show how to build some code, a Dockerfile gives instruction explaining how to build a container. Except that we wanted Docker files to be easy to write, in the sense that, well, makefiles are not too complicated, but generally people don't really enjoy writing them. Deployment scripts, that's kind of the same issue. So we wanted Docker files to be easy enough so that a developer, when they have to ship their code and they are told you have to write a Docker file, they will say, oh yeah, sure, no problem. Instead of, oh crap, I have to write some recipes and everything, and you know. So the idea is that we indicate a base image. So in that case, we were using Ubuntu, and then we indicate a bunch of commands that we want to run into that image to build our service. So in that case, I picked an extremely simple build process where I just install the Nginx package and I generate a small HTML file. But here you could have run something to install Java, run something to clone my code from my repository, run something to actually build that code, run something to generate configuration files, and so on and so forth. And then I have some extra information to tell to Docker what command should be executed when the container starts, and what TCP ports are exposed. We are giving some kind of extra information. It's, I mean, the same way that when you give like a Java jar file to someone, they know that if they do java-jar something, they will be able to start it. It won't tell them if the thing is listening on some TCP port. It won't tell them if it expects some storage to be available. So it still requires some extra information. And when you need to restart it, same thing. What do I do? Do I kill the process and restart it? Or so the idea around containers was also to help with that. As a member of the ops team, when you receive a container and you know, how do I start this program? Well, you just start the container, and I will show what this looks like. Okay, so I have two Docker machines, John and Yoko, and this is Yoko. And so here I have my simple a Docker file. That's pretty much the same one. And I'm going to build that Docker file. It's as simple as docker build. I will call that web. And I want to build the current directory. And so it will execute each step, so that's the apt-get update. And at the end of that step, it will take a snapshot of the result of that step, and then it will execute the next step, which is installing Nginx. Faster, now, the next step, which is executing Nginx. And after that step, it will also take a snapshot, and then execute the next step, and so on and so on. The whole point is that if I change my recipe, my Docker file, if I change my source code, if I were using some source code here, when I would redo the Docker build, Docker would be smart enough to only re-execute what it needs, makefile style. And that should be a little bit faster. So the first build will be a little bit slower because it ends up installing all those packages, all those dependencies, and doing all that heavy work. But it's not a problem because once this is done, the next builds will be much faster. So now let's start this container. So this means start it in the background, expose all the ports, and then, okay, it's on that port. So now I go to my web browser, and then I put the right port number and say, okay, that's my hello world, so that's my microservice that echoes hello world, so it's not extremely exciting, but for demo purposes, it's not too bad. Now, I want to show this clever build method I was talking about. If I do, hi, Cisco, I'm in your container, and now I rebuild. This time, it was almost instant, because Docker knew that I already did apt-get update on top of this. I already did apt-get install Nginx on top of that. And then here, it said, okay, that's a new step. I don't have the result of that command, so I'm going to execute that command. But it's okay because that step is fast. So if you put all the heavy steps, all the expensive, slow package installation stuff in the beginning, and all the stuff that changes a lot toward the end of the recipe, then your rebuilds will be extremely fast. And now, of course, I can start the new container, right? It will be on a different port, right? It's the next one, that's convenient. And, right. And so here, quick plug about immutable infrastructure. If I realize that I really messed up my deployment, I shouldn't have done that, and I need to roll back immediately, I don't have to re-edit my Docker file, change and rebuild and rerun. No, because the old container is still running, so I can still get back to it. It's just on the other port. That means that when I need to make a rollback because I rolled out a feature and in fact I rolled out a bug and I really need to go back to the version we had yesterday, that's okay because I still have that image which can be either still running in that case or ready to run. If this were in a production scenario, I wouldn't be hitting that IP address and that completely weird port. I would have a load balancer in front of that pointing to the right port. And when I do my deploy, at the end of the deploy, I could check that everything is fine and then reconfigure the load balancer to send the traffic on the correct port. And if something goes bad, I can reconfigure the load balancer to go back. Right, so that's the part about building. Now let's talk about shipping. So what does it mean to ship a container? Well, there is something called the Docker Hub, and so many people, when they start to use Docker, use what I just showed here, this kind of Docker tool, which is actually the Docker engine, and is only half of the thing. The other half is about moving things around, sharing code and builds, and that's what the Hub does. And I will also demo that. So I did my build on that machine, on Yoko, and I want to run that on John now. So I will retag this, so that's Petazzoni as Cisco demo. And now I will push it. And so that will take maybe a minute or something. And so the idea is that, so to do that before I prepare my machines and I logged in on the Hub, so this is not like an anonymous thing, this is using my Docker Hub account. And so that lets you share container images with other people. either publicly, so in that case it's a public image, so anybody could from their Docker host do Docker run Petazzoni/Cisco demo and they would get the same container. But I could also use a private image because not all the code we write is open source and designed to be published to the world. And so we also support that. So now I'm going to check the other machine. And I will do Docker run, so -d-b Petazzoni/Cisco demo. So that thing doesn't exist locally, so it's pulling it from the hub, and after a minute or so, it will be up and running. So the idea is that you could rebuild your image everywhere, and it should kind of work, and phases on should, because there might be a little difference. Maybe you have one of the machines is in Europe, the other is in the US, and so they use different package mirrors, and one of the package mirrors has not exactly the same version. So by sharing images instead of sharing recipes, you can be sure that what you run is exactly the right thing. It's the equivalent of taking a VM image and giving it to someone on a USB stick or uploading it somewhere. They will start it and it will be exactly the same thing. Okay, so now this is running. The problem is I have no idea of the IP address of the other machine. Yep, yes, copy, and I go there, and now, surprise, surprise, what was the port number? 1913. Right, so now I have exactly the same image running on the machine. So that's the shipping part. So now we have something so that we can easily build our microservices. We can move them across, and yeah, and it's magic. So the third part is run containers. So the emphasis here is that, okay, we have something to run our code, but is there any kind of overhead, any downside to running code in containers? So a lot of people did benchmarks. And those benchmarks are very interesting. So first, I did myself a very small benchmark. I checked, okay, how long does it take to create a completely useless container that just echoes hello world? It takes like 2 point something tenth of a second, so that's pretty fast. And when you do that, your disk usage increases by less than 100 kilobytes and memory footprint by just a couple of megabytes. So that's really lightweight. Compared to VMs, even if you really fine-tune your VMs, they will take maybe 5-6 seconds to boot, but definitely not 1/10 of a second. And the disk memory usage will be much bigger. It's not to say that containers are better or anything like that. I will get to the point very shortly. Whoops, no, sorry, not like that. So then there are benchmarks about like latency and network bandwidth, showing that there is no difference between physical machines and containers. Then this is a benchmark comparing containers and VMs, showing that containers boot much faster and use less memory, so that's great. This is also a benchmark comparing bare metal, Docker, and VMs. And again, we see that there is no difference between containers and physical machines, but that the VMs take a performance hit. So yeah, containers are really lightweight. And so I just want to also show that in action rather than just showing benchmark, but basically going to do, okay, Docker run Ubuntu bash. So I'm starting an Ubuntu container. That was really fast. And now I'm going to start a bunch of those containers. Okay. Well, I'm just limited by the speed at which I can mash the keys. So yeah, in just a few seconds, I started 10 containers, and the resource usage on the machine is still almost nothing. It's, yeah, like as if nothing was happening on the machine. So the point is not to say that, okay, containers are great, let's throw away VMs. No. The point is to explain that it's okay to put things into containers because you're not paying an extra virtualization tax on your containers. The point is not to replace VMs with containers. The point is to say it's not VMs or containers, it's VMs and containers. Because we can put containers inside of VMs without adding any kind of overhead. And if we have, in some scenarios, if we have a big compute cluster and we did some benchmarks and we realize that we have a 5% overhead because of virtualization, then we can think, well, maybe I want to switch to containers because I have 10,000 nodes in that cluster. 5%, that's like 500 nodes. So it means that in my data centers, I have a few racks that are full of machines that are just doing virtualization stuff. I mean, it's not exactly what happens. It's like spread out across my whole cluster. But symbolically speaking, it means I have a few racks full of machines just to pay the virtualization tax. If I'm in that scenario, it makes sense to switch to containers exclusively instead of VMs. But if my cluster is just like 100 machines, that virtualization tax is 5 nodes, so it's okay. I can afford that. So now we said that we would be able to run any application. What does it mean exactly? It means that if it runs on Linux, it will run in Docker because it's just running Linux processes, so there is no limit to what you can run. So the traditional use case was server workloads, web applications, web servers, backends or APIs, databases, whatever, whether it's SQL, NoSQL, big data, message queue, anything that you typically run on some VM or server, you can run in a container. And some people tried some fancy things. I played guilty. So trying to run like a browser inside of a container, which sounds a little bit crazy, except that when you run a Linux machine, browser vendors all suck completely. So I have Chrome, but the median time to crash of Chrome is less than 1 hour on this machine for some unknown reason. The median time to I'm using all your RAM and you have to restart on Firefox is maybe 4 hours. So all browsers on Linux suck completely, except if you have exactly the right combination of libraries, the right combination of everything that those people are using, and then things more or less work. So the idea was, okay, but I don't want to stick to those exact versions because maybe I want to run Skype and Chrome and they use different versions of something. So what do? Well, I put them in containers so that each application can have its own set of libraries, its own set of dependencies, and I'm no longer stuck because I have incompatibilities, which is more or less what happens on OS X when you install an application. It actually comes with most of the dependencies bundled in. In some way, OS X is already using containers to ship applications. So Firefox is an example. Xorg, the display server, runs in Docker as well. Network appliances like VPN, client and servers, firewalls, content filters. You can even run Docker and Docker, and you can run KVM virtual machines in Docker. So if you want, you can run Docker in a VM in Docker, which leads to pretty confusing results, but it always a fun demo, but that I won't do that time. And so the last part of the Docker model, build, ship, and run any app anywhere, is the anywhere. So I mentioned that earlier. Limitations may apply in the sense that officially Docker supports Intel 64-bit platforms, and that not the 64-bit Italian, the 64 bits, the common one that we all use, and only recent kernels, like that means 3.8. The great thing is that last year when we were doing the first demos of Docker, 3.8 was really bleeding edge, so people were like, no, I'm not going to test your stuff because my kernel is like 2.6, you guys want 3.8, that's not gonna fly. Today, virtually everybody, I mean, all the major distros have at least 3.8 or even 10 or 12, so we're good. Microsoft announced a couple of months ago that they would support containers on Windows, so that was kind of a surprise even for us, because one of the usual things was like, oh, you can run anything except Windows applications, of course, it's not true anymore. Now, soon we'll be able to run Windows workloads inside of Docker. That doesn't mean that you will be able to run Windows app on Linux. That doesn't mean that you will be able to run Linux app on Windows. It means that you will be able to run Linux apps on Linux and Windows apps on Windows, but they will be in containers that you will be able to deploy, control, manage, supervise, orchestrate, and so on using the same API. So using the same command line that I was showing, Docker run this, Docker build that, Docker pull and push, you will be able to do that on Linux and on Windows. So from the ops point of view, there will be no difference between Windows app and Linux app. That should be great. Some people, so rumors, as in a lot of people actually do that, but we don't support it. have been running Docker on older Intel 32-bit machines, on ARM 32 and 64 bits. There is a French hosting company online. We just started a kind of on a physical cloud. So it looks like a cloud. You can spin up instance and they boot really fast and everything. So it looks like VMs, but it's actually physical machines using ARM64. And they have Docker all over the place. MIPS, power rate. You can also run with older kernels, but please, please, please don't do it, because in the beginning, like, yeah, I'm stuck with kernel 3.2 and they said I needed 3.8, but I'm testing and it kind of works until things go and crash and burn, and then don't tell that we didn't warn you. There are lots of things that were improved in the more recent kernels to help with containerization. So that's why 3.8 bare minimum. And if you can afford it, just have the latest kernel you can, because performance and reliability and security and stability will be much better. One thing to know is that the Docker Hub registry is not archware. So what does that mean? It means that, for instance, when I did my Docker push of my little web application, and then I put it elsewhere, if those had been two different architectures, that wouldn't have worked at all. I can't build an Intel 64-bit container and then try to run it on some ARM64 or Intel 32 machine. That won't work. However, the Docker file might be compatible, because that basically is source code. You can really think of it as the Docker file being the source code, the recipe for your container, and then the container itself being the binary that you run. So, containers, stacks of containers. So how do we run multiple containers? Because that's nice. I kind of showed, okay, we have a kind of new packaging format that's containers. So basically all the ops persons and sysadmins are like, well, that guy sucks. We have packages and they work great. So why are we bothering about containers? So it will get more interesting for that group, and we will start talking about running multiple containers at a time. So where is it? After that, sorry. Yeah, I have a kind of checklist of how to get started with Docker, and then I will have a demo of running multiple containers at a time. So when you want to try Docker, there is an online tutorial which is like completely JavaScript browser side, so you have nothing to install. Obviously, it's not the real thing, it's just a mock-up of the CLI in JS. Then there is boot to Docker. Boot to Docker is awesome because I think it's the smallest useful VM image ever. I mean, I've never seen a VM image smaller than 50 meg that would still be useful for something. So boot to Docker is like 25, well maybe it got a little bit bigger, or maybe 30, but it's still small enough so that when you need to just download it, you download it and in seconds you get it. It's not like this 300 megs VM. It's a VM image that is kind of universal because it works in any kind of virtualization platform. You can use it on VMware, you can use it on VirtualBox, you can use it on Parallels, on Xen, on KVM. You can also put that on a USB stick, flash drive, or a CD and boot physical machines with it if you want. And it's both like the test environment that you can use when you want the real Docker thing, and also the official development platform. So when people are working on Docker on non-Linux machines, that's what they use. It's not like the trial lightweight version of Docker, it's the real thing. When you want to install Docker on your actual servers, there are two methods. Well, we have normal packages, but you know how distros are, they tend to lag a little bit behind the versions, and Docker is a pretty active project. We have a new version like every month, every 2 months now, and that's still pretty fast for most distros. So we also have an extremely scary install script, but basically you run that line and it will take care of installing Docker on your machine. And then that's kind of a security issue in some way, because if we decide to put some nasty stuff in that script, you might have problems. But you can download the script and review it and then run it if you want, of course. So the kind of zero to hero with Docker is, so first install boot to Docker, run your first container, it's just like Docker run ubuntu echo hello world, because if it works, it means that your Docker install works and you can go on. Then write your first Docker file, so take your application and try to write Docker file for that application, which is not very hard, because if you know how to write a shell script, You take that shell script, you put from in the beginning with the distro that you want to use, you add run in front of every line in your shell script, and you're more or less done. Then you create your Docker Hub account so that you can push your image and check that everything works. Then you can set up automated builds. Automated builds are a kind of a gateway drug to continuous testing and continuous deployment and continuous integration, because basically that's a feature that lets you link together a GitHub repo and a Docker Hub repo, so that each time you push to your GitHub repo, it will trigger automatically a build and make the result of the build available on the Docker Hub. So you can literally push, and a couple of minutes later, you go to any Docker machine and you do Docker run blah blah blah, and it will pull the latest version and run it. And the next step, once you have that, is okay, how do we actually compose stacks of containers? How do we build complex apps? Because in the beginning I said, oh yeah, we have a platform with 106 services, but so far we only saw one. So then we use something called Fig. Fig is a system that allows you to describe a stack in a YAML file that looks like, that should be smaller, that's just a part of the file, but that's not the problem. So you have a YAML file describing all your services, all your containers. So in that case, the goal is to run a Mesos cluster. Mesos is a large-scale orchestration mechanism which has been written and is in production at this small garage startup called Twitter. And so they decided to make it open source. It's an Apache project now, and there are a bunch of people contributing to it. And it's the kind of stuff you want to use when you have a few thousands of machines, and you're starting to say, well, apparently, according to my ops team, we are wasting a few CPU cycles here and there because the average usage on the cluster is like 15%. And again, 15% is a lot. Generally, it's more like 5 or even less than that, which means that like 90% of the IT budget here is wasted. That's not very good, just as your CFO. So those folks wrote Mesos, and the result was that after a few months, they managed to divide by 2 or 3, I think, their Amazon bill for some projects. So that's fairly nice. And anyway, so the point of Fig is that you just describe your stack, like container per container. You indicate what you want to run, the connections between the containers, and then you just do one command, and it will bring everything together. And that will look like this. So this is my Fig YAML file, and I will do Fig up. So Fig will automatically tell Docker to pull the required images, and I should have done that before so that it doesn't take a minute, but that's fast enough. It will start the containers in the right order. So if you have dependencies, like you have a database in your front end, to make sure that the database is up and running first. And then it will start the whole stack and give you the output of that stack. Faster, please. And once it will be up, there will be a web front end. So yeah, this is kind of a weird demo because we are demoing Fig, which is an orchestration system for stacks on an individual machine, to bring up Mesos, which is an orchestration system for large-scale clusters. And on top of Mesos, we run Vault, which is a kind of, let's say, a front end for Mesos. And not yet, almost. Yep, we have the master, the slave, and now it's pulling down Vault itself. There was a question about Kubernetes in the beginning. So in some way, you can see Mesos and Kubernetes as competitors, even though to make things more confusing for everybody, there is also integration between both. I can talk pretty easily about Mesos. I can talk about Kubernetes. However, I don't know exactly how they mix together. That's still the mystery to me. But I hope to learn more about that soon. Right, almost there. And so once this is up, not only we will have a Mesos cluster running on this machine, but we will also have a small web interface to actually talk to that Mesos cluster. So, right. And there is more. Right. So that's the output of all the different services with a prefix indicating that this is the output from slave, this is the output from vault, there is probably some master laying on the top. And so if I remember correctly, we should go to the other tab. I can do this. No. No. Okay, keyboard, right. And it's on port 8080. No. Whoa. I might need some help here because I don't know what I did.
Help is on the way.
That's why I should never be allowed to be within the vicinity of a Windows machine. I always end up breaking things.
Password is password, right?
All right, thanks. I'm sorry about that. All right, so now we have, yeah, that's the web front end for Vault. And so it tells me that I have some CPU, some disk, some memory, and I want to run something. So I want to have something using half a CPU and 128 MB of RAM. I don't need disks, and I want to run Redis. And I don't want to specify a given command, and I send this. So already, that's too fast. That's highly suspicious. Now that's it. If you ever ran Redis at least once, you might remember this. This is the default output of the Redis service when it starts. So what happened here? I'd like to try to explain a little bit. So we put that in the background and do Docker PS. So it would be a little bit better if I do like this. So we still have the first two web servers saying hello world and hello Cisco running here. Now I have the Mesos master, I have the Mesos slave, I have Vault, which is part of that whole thing, and now I have also the Redis container that we just started. So we kind of added a management layer on top of our Docker machine, so that instead of doing Docker commands, we could go to that web interface and add things. The great thing is not that there is a web interface. The web interface is just here for demo purposes, because the web interface is one of those single page HTML5 apps, which means that it's just static HTML and it's doing AJAX requests to an API endpoint. So Vault is actually an API endpoint where you can send requests to say, start this Redis container. And if instead of one machine I had multiple machines, then Mesos would kick in and say, okay, you want to start something with 5 cores, let's find somewhere a machine that actually has 5 cores available. Or you want to start 10 instances of that web front end, let's find 10 different machines to run that web front end. So that takes care of scheduling and resource scheduling and orchestration on your cluster. All right, so what's next? So yeah, that's the future of Docker and containers, nice and shiny. Some advanced topics. So I deliberately say, okay, I'm not going to talk about load balancing and service discovery because that could honestly be a full talk by itself, and there is already quite a lot of resources available about that. But it's not exactly directly intrinsic to Docker. I mean, if you want to do microservices, you have to have some service discovery and registration at some point, and whether you have containers or something else, the problem will be pretty much the same. There are some very interesting ways to solve that with Docker, but it's kind of more advanced. Some of the things that you will want to do when you start to play with Docker is that you will say, well, the Docker Hub that guy demoed is nice, but I don't want to push my code to some third party. That doesn't fly. So that's fine. The registry, so the registry being the part responsible for storing container images, is open source, and you can run it locally if you want. So if you don't want your code and your builds to exit your data center or your firewall, you can run the registry locally. There are often lots of questions about containers and security, so there are a bunch of articles about that, and yeah, that's pretty much it. Thanks a lot. If you have questions, I will be extremely happy to try to answer them. Yeah.
One is that the bootloader uses the VM. Does it support the VMX.NET 3 with IO or the C1000 simulation?
So boot2docker is a VM, and does it support, you said?
Can you
What
repeat?
is the Ethernet emulation? The
Uh,
virtual interface.
Oh, virtual interfaces. Does boot2docker support virtual interfaces? You mean, can I use like PCI pass-through or something like that?
Or do you support VMX.NET 3 and what are the drivers? that
Oh,
are
what network drivers are available on boot2docker? That's a good question. I don't know. I would reasonably suppose that there is like VirtIO and well, all the stuff that kind of ships with the default Linux kernel, which I think is not the case of neither the VirtualBox extensions or the VMware extensions. So, no, that's a good question, and I wonder if CoreOS, which is another kind of Docker distro, will help with that. Worst case scenario, I would say, people sometimes ask, what's the perfect Docker host? What's the perfect distro? Should I use CoreOS because it seems to be dedicated to running containers? The answer is use whatever you are already using. If you're already standardizing on CentOS, use CentOS. If you're using Debian, continue to use Debian because Docker will run anywhere. Then there are a couple of specific options. Boot2Docker